I'm going to talk about some rather old topics. These are things I thought about some time ago, and I've sort of discovered that when I first think about things, I understand them very clearly. And then with time, I come to understand them less and less well. And unfortunately, these are all topics I've thought about for a long time, so I'm extremely confused. And so I hope to leave you equally confused. The topics that I'm going to talk about are rather different. They're possibly related to hydrodynamics, but not asking the question, where can we find hydrodynamic behavior because we're interested in hydrodynamics, but rather, are there peculiar transport phenomena that we haven't been able to understand that maybe thinking about them from a hydrodynamic point of view might give us some new insight into them and some new ways of understanding them. There are two different anomalous transport regimes I'm going to talk about. One is the unexpected metal in strongly interacting two-dimensional electron gases. And the other is bad metallic behavior in cuprates and other highly correlated electronic materials. The question is whether we could understand either, get any insight into these by thinking about electron hydrodynamics. I think the first topic that I'll talk about today is this one, and the answer there is maybe. And the second is the strongly correlated systems, which I'll talk about in my next lecture, and I think the answer there is probably not. The other thing I should say is that I come from a somewhat different labor union than most of the people here. I tend to think about equilibrium properties of systems. If I'm really, really forced to, I might say some things about near equilibrium properties in the context of linear response theory. I'm not used to thinking about mesoscopic systems, although presumably equilibrium properties have some consequences there, and I'm absolutely terrified of systems far from equilibrium. We have enough of that in our political life. Let me talk about the unexpected metal. This is, to the extent I'll talk about my work, it's work done in collaboration with Boris Spivak. And from some time ago, we have a brief review article in Reviews of Modern Physics. So this is a topic that looks, at least to begin with, promising for hydrodynamics. It's related to what's going on in the cleanest two-dimensional electron gases in the limit where the interactions are very strong, which should be a promising limit for hydrodynamics. This is an old problem, but it's probably so old that most of the students here don't know anything about it. I'd like to say that it's old enough to be new again. Okay, so I was having trouble. I didn't have time to prepare, so I had to steal transparencies from old talks. And I left this one here because there are a couple of things I want to boast about on this. This is from a talk I gave at a conference in Korea in 2013. And firstly, I noticed that, with PowerPoint, people tend to show pictures of, Einstein and Fermi, and then pictures of their collaborators. And the clear observation is that, their collaborators and they and Einstein and Fermi, they're all sort of the same. Well, I at least thought that I want to show pictures of what I wished my collaborators looked like. So the other thing I wanted to boast about was I gave this talk on hydrodynamics. It was...
Exactly.
What?
We were all wondering which one's Boris.
I gave this talk on hydrodynamics, and I think I was ahead of my time. The conference organizer reviewed my talk, telling me that I was bloviating. I didn't know what bloviating meant, so I had to go to the archive to find it out. It means to talk at length, especially in an inflated and empty way. I thought that was a pretty impressive insult. Good. So here are some references. So, okay, so in this audience, I don't really have to review hydrodynamics, but just I'm going to run through some things really quickly to orient ourselves for why this might be a reasonable approach to the problem. So, well, hydrodynamics, as we know, is slow dynamics associated with conserved quantities, and in particular in fluids, that's energy, momentum, particle number. And it gives us descriptions in terms of the thermodynamics of the fluid, and then in terms of a few transport coefficients, the viscosity, the second viscosity, the thermal conductivity. And this is very different from the sort of description we're used to in solids, where we talk about things like the resistivity. So the other thing about hydrodynamics is that it's one of these universal features of physics that we like. In a Galilean invariant system, hydrodynamic description is universally applicable as long as we're looking at long enough distance scales and low enough wave numbers.
You don't need Galilean invariance. For example, in curved space, you don't have Galilean invariance, but you do have hydrodynamics. It's more general.
That's fine, but it's certainly true under these circumstances. So this is not the case for electrons in solids. Electrons in solids really, in principle, don't have an asymptotic hydrodynamic description. Momentum and energy are exchanged with phonons. Momentum is lost to the lattice through Umklapp scattering, and as Andy mentioned, experimentalists refuse to make perfect samples, so there always are some impurity scattering. So at most, hydrodynamics can be an intermediate scale description of the physics of electrons in solids. And so from this point of view, ultra-high mobility two-dimensional electron gases in MOSFETs and other heterostructures seem like a good idea, because at least one of the sources of problems is gone. There's no, the Umklapp scattering is unimportant because the Fermi wave vector is extremely small compared to a reciprocal lattice vector. If they're very clean, it invites us to think that maybe impurity scattering can be made unimportant, or at least important only on very long scales. And we know that if we go to low enough temperatures, the electron-phonon coupling becomes increasingly quenched. In fact, this is what limits the ability to do experiments at low temperature. The electrons simply fall out of equilibrium with the material. So if the mobility is high enough, if the impurity scattering is weak enough, then we should be able to find a hydrodynamic regime where the temperature is low enough that the electron-phonon scattering rate is very small, small compared to the electron-electron scattering rate, but still high enough that the electron-electron scattering rate is large compared to the impurity scattering rate. So we're going to look for an intermediate range of temperatures given by these sorts of things. Even in this regime, if you're a bulk person, it doesn't mean you have hydrodynamics. It just means that hydrodynamics applies at intermediate distances. At long enough distances, we're still going to have ohmic physics. And as Leonid explained to us, that's something like the square root of the bad length times the electron-electron scattering length. Okay, good. No, well, this is where I want some magic to happen, so I go to, yes, important collaborators. Okay, so suppose we do have such a problem, maybe that we have a problem where we can totally ignore electron-phonon scattering, and the only source of momentum damping is given by maybe some very long wavelength, large-scale obstructions to the system. Then we would get that the resistivity would be determined by the viscosity. I would still have ohmic behavior. I would still have a resistivity, but this intermediate scale hydrodynamics would be reflected in the fact that the resistivity then would be geometric factors, which have to do with the distribution of these large-scale barriers, times the intrinsic viscosity of our fluid. And as several people have commented, this just sort of blows your mind. It gives behavior that's totally unexpected. It tells you, well, suppose your fluid is a Fermi liquid. In a Fermi liquid, the viscosity goes like 1/t squared, which means that if we were in this cleanest of all possible metals with resistivities tiny compared to the quantum of resistance, we would have a insulating temperature dependence of the resistance, in the sense that we would see the resistance starting to grow as we lower the temperature. So it really is a very different transport regime than we're used to. They're going from the hydrodynamic description to the resistivity is complicated. There's all sorts of different cases depending upon how you introduce momentum non-conserving features. I just wanted to give one other example because it was mentioned during Leonid's talk. So we considered at some stage what happens if you have a system with smoothly varying disorder of some sort, but weak. And then in 2 dimensions, it's possible to obtain an expression for the resistivity that goes like this. So let me just explain what the answer is. The derivation just comes from the Navier-Stokes equation, so it's straightforward, although, well, okay. So here, these are equilibrium properties. So this is the mean squared gradients of the inverse density in equilibrium. And this is the mean squared variation in the local entropy density. Those are the things that the hydrodynamic flow responds to, and then this is a linear response expression. This is what happens if we look in the limit of very small average velocities. How much force do we have to apply on the system to get the current to flow? And the sort of surprising thing here is this term that's proportional to the inverse of the thermal conductivity. The reason that comes in is that, as I think was mentioned the first day, in some approximation, you might think of hydrodynamic flow as being adiabatic, as being along contours of constant entropy. If that's the case, then a region where the entropy of the fluid changes acts as an impenetrable barrier. And so unless you have some way of relaxing the entropy, there's no way to get past these entropic barriers. So that's a little bit of an unusual expression for a resistivity.
This has probably hidden temperature dependencies in many places.
So, so certainly the entropy density is temperature dependent,
And also the viscosity.
and the viscosity and the thermal conductivity.
So once you put everything in, what kind of temperature dependence?
It depends on what system you're looking at. So this, in a Fermi liquid, this will have a T squared here.
Overall term is T to the 4.
What?
Overall, it's T to the 4.
This term is T to the...
Overall, yes. So T1 over the temperature for thermal conductivity,
Yeah.
T squared.
In the first term?
And that one is 1 over T squared.
For a Fermi liquid.
What is it's non-monotonic. It drops down, but then it goes up.
Right.
What's zeta?
That's the second viscosity. So since I'm allowing density variations, I'm considering a compressible fluid here. So both the first and second viscosity come in. Thank you. What?
Where is its order in this expression?
So that's this. These are the averages over the disorder, but of thermodynamic quantities, of equilibrium properties. So you look at the system at equilibrium, you measure the equilibrium density, you calculate its gradients, you take the mean squared of that, you calculate the mean squared of the entropy density fluctuations, you calculate that. These are in turn complicated functions of the underlying disorder.
And what is the first?
What?
What are the first and second viscosity? What is the second viscosity?
The second viscosity is the dissipative term coming from compressional motion. So it's a term proportional to del dot V in the dissipation. And it's often left out because you're often dealing with incompressible fluids where it doesn't arise. All right, good.
Viscosity multiplies the gradient of density, not only volume viscosity. It's 0 for incompressible case, right?
So this term would be 0. There wouldn't, if this were an incompressible fluid, I wouldn't have any density variations here.
It's strange that eta also in front of it because it's shear viscosity, which
Yeah, well, this is gradients of the density that come in. Okay, good. So, so that's my introduction. I'm now getting to the main part of the talk, and so okay. So as I said, this is the place where if you knew nothing about experiment, but just were thinking about the issue of where would you expect to find hydrodynamic effects, this would be the best place to do it. It's a place where, in principle, if you work hard enough and make the system clean enough, you can make your hydrodynamic regime as big as you like. So I've already said those two things. The reason I would like to have a large RS is, as Andy pointed out, if we calculate electron-electron scattering rates in good metals, we tend to find that they're extremely small. The electron-electron mean free path is extremely large. And so although I've made bold words about wanting to look at bulk properties, they're going to be inaccessible there. I would like to look at systems where the electron-electron scattering rate is large, where the electron-electron mean free path is really small, so that I only have to have these other length scales somewhat large to have a hydrodynamic regime. And so that drives us to look at the cleanest systems we can, but also the most strongly interacting systems we can. So I just want to remind you of this this parameter that characterizes the strength of the interactions in a two-dimensional system. We define RS generally as being the ratio of some typical electron-electron interaction to some typical kinetic energy. And so in a two-dimensional system, maybe we estimate the typical interaction energy by calculating the Coulomb energy in the Hartree-Fock approximation. For the kinetic energy, we take the bare Fermi energy. Once the interactions get strong, you can worry about both of these, but okay, it's a characterization of the strength of the interactions. So the ratio of these goes like 1 over square root of pi. The square root of pi is what comes from doing this explicit calculation, but times the density times the effective Bohr radius squared, where the effective Bohr radius is the Bohr radius with the mass of the electron replaced by the effective mass in the semiconductor, and with the effective charge squared replaced by the charge squared over the dielectric constant. Okay, so what that means is that if I want to look at strongly interacting electron systems in two dimensions, I want to go to low electron density. Now, for low enough electron density, we're not going to have any interesting hydrodynamics. In principle, we're going to have a Wigner crystal when the Coulomb energy dominates. But for reasons that, well, that I don't really understand, there does exist this regime called strongly correlated electron fluids, in which RS is much bigger than 1, so that the interaction energy is very large compared to the kinetic energy, and yet the system remains a fluid. Theoretical estimates of the critical value of RS in two dimensions put this critical value at 30. I'm not sure I believe that one really has such good theoretical control that one can talk about this number, but it's certainly a number that's quite large compared to 1. So there is a broad region where the interactions are indeed very strong compared to the kinetic energy, where all of normal solid-state physics is questionable, and yet where we're still dealing with a fluid. And so, although I'm not sure that using Fermi liquid expressions for the equilibration rate is a reasonable thing here, I think it's quite reasonable to imagine that in this case the interactions are strong and hence local equilibrium is reached rapidly. Good. So let's just look at experiments and see what happens when we look, yeah?
So in the typical Fermi liquid expression, we have T squared over E Fermi, but no mentioning of RS. Where would it come in?
Yeah, that's interesting. So, I mean, the fact that it's T squared over EF has always been puzzling to me. It's because we put in the RPA screened Coulomb interaction and the Coulomb energy cancels out. So, in fact, in the Fermi liquid expression, the only place it would come in was that EF in this case would be a renormalized EF, and presumably as we turn, so first place we're starting with that relatively small because we have a low electron density, but also we would expect some large mass renormalizations due to the Coulomb energy. So here in the renormalized value of EF would be where the strength of the electron-electron interactions would come in. But obviously, if Fermi liquid theory is breaking down, then all bets are off on this.
And the renormalized value would not necessarily go down. Like if I think of 1D example, I add interaction, I basically boost up all the energies up, not down.
So 1D, you destroy Fermi liquid theory. Yeah. But in two dimensions, essentially every effect I know enhances the mass. You're dragging, it means as you move a quasi-particle, you're dragging all sorts of other stuff along. And so the effective mass goes up. If the effective mass goes up, the effective Fermi energy goes down. Okay, I don't want to make too much of it because in this regime, both on theoretical grounds and on experimental grounds, I don't think Fermi liquid theory applies. So let's ask, what do you see when you look at the properties of two-dimensional electron gases at large RS? And so, well, there was some very famous work by Sergei Kravchenko in 1994. Here's some pictures. This is from silicon MOSFETs. As I understand it, these were made in some top secret Soviet military establishment, but at any rate, these are curves for different electron density. This is temperature. This is log of the resistance here. And the thing that struck everybody was that there occurred a metal insulator transition, that these somewhat higher density curves have a metallic temperature dependence. These somewhat lower electron density curves have an insulating temperature dependence. And all of the discussion was about how could we have a theory of this metal insulator transition. These are all at low electron density. The range of RS's in these curves goes from 14 to 19 here. Here's the quantum of resistance. If you want to, this is resistance in units of the quantum of resistance. So these are all things that are in a very difficult regime for transport theory, where the resistance is on the order of the quantum of resistance. Since then, similar phenomena have been seen in a variety of other two-dimensional electron gases at low electron density. Here's data on p-type gallium arsenide, gallium aluminum arsenide heterostructures. This is for a wider range of RS, in this case from 12 to 32. And again, you see this metal insulator transition occurring, where you get these metallic behaviors here, and you have this insulating behavior there. And here's in N-type silicon germanium heterostructures. And again, this is a log scale. And I'm going to come back to that, but you know, this doesn't look all that impressive because this is a log. But if you look over here, you've got variations of an order of magnitude of the resistivity. And even here, you've got variations of factors of 2. So these are not small effects. We're not looking at little bitty things that you have to zoom in on. These are very big changes in the resistance with temperature.
So this is at RS, which you'd expect to be already above.
Yeah, you know, there's even some ambiguity about what you mean by RS. So RS in a single pocket system with an isotropic effective mass, okay, we can report them, but when you have multiple pockets, it's not exactly clear even what you're supposed to mean by RS. So really, I don't want you to pay, I mean, these, the numbers I'm quoting are the numbers quoted shows on my screen. I think it's thinking about it somehow. Okay, so the values of RS I'm quoting here are what the experimentalists say in their paper, because I didn't want to have to think about it. But for my purpose, it's just that it's big.
actually these systems still have some amount of disorder. So when you reach the high side of RSS, you're already really disordered in this sense. So you would not expect really a big increase.
Okay, so so the reason people got so hot and bothered about this is that there was a strong ideology that metals can't exist in 2 dimensions, and, well, people were sort of willing to accept that things that were operationally metals might exist. But the existence of a metal insulator transition, you know, if there's a transition, then there really has to be a phase, and so calling this a metal insulator transition seems to imply that it's really, truly, honestly, in, you know, some textbook sense, a metallic phase we're talking about, and that was very upsetting to most people. But this is a problem that theory was able to resolve. We changed the name to the apparent metal insulator transition, and everybody's happy. I actually have a serious point to make here, which is that there's a funny business in our field where a theory, of course, can be judged regardless of whether it has or ever will have anything to do with experiment. But experiments somehow are not considered to be respectable unless they can be accounted for well by a theory. And you know, that's not totally wrong. I mean, theory does give us some insight into things, but I think it is important also to be very careful about saying what you actually see in the experiment and not, you know, then we can try to reconcile it with our theoretical prejudices, but the experimental statements need to be made clearly without being overly influenced by theory. So I'm not going to address the issue of the metal insulator transition at all. I'm not going to address the issue of whether really at 0 temperature in the thermodynamic limit this metal exists at all. What I would like to do is focus on the metallic phase that's seen in these materials and to show you that that metallic phase is extremely anomalous and that understanding the transport and the nature of that metallic phase is well worthwhile. Okay, so what I want to do is I want to focus on these metallic samples, and ideally I would like to look at the metallic samples that are well on the metallic side of the transition. So here's a resistance that's of the order that's equal to the quantum of resistance. So here are samples with resistance that are 10 times smaller than the quantum of resistance, where if this were Fermi liquid behavior, you would think that we would be able to understand these very simply on the basis of theory. And so what I would like to show you is that in many ways the behavior down here is entirely unaccounted for by conventional theories and requires some serious new understanding. Unfortunately, I had a hard time finding plots where this is plotted on a linear scale. You know, this is a very nice plot for showing that there's a metal insulator transition, but if I want to look at the properties of the metal, I would like to see things on a linear scale. So here's for the silicon MOSFET on a linear scale, but all of the interesting things are squeezed down at the bottom here. But what you can see is that there's, well, a factor of 5 at least value change of the resistance at a temperature that's too low for phonons to matter. It's well below the Fermi energy, which in this case is 7.5 Kelvin. It's actually more or less linear with temperature, which gets some people excited. Here's a gallium arsenide, a p-type gallium arsenide heterostructure. Here's some calculation that they did of what you would expect within Fermi liquid theory from electron phonon scattering, and you see that the resistance has nothing to do with that. Here's the holes in this p-type silicon germanium heterostructure. Again, you see, well, in this case, more like a factor of 2 variation with a more or less linear temperature dependence. Conventional theory wouldn't give you any particular way to understand this temperature dependence at low temperature. Now, there's something even more striking, which is the magnetic field dependence. So here, this is applying a magnetic field in plane. And so presumably, to good approximation, the in-plane magnetic field only couples to the electron spins. So what I'm showing you here is the effect of polarizing the electron spins. And so we can understand why these curves become flat at high magnetic field, because presumably at this point you've polarized all the electron spins. And in fact, from the value of the field at which you achieve this saturation, you can measure something like a Fermi energy. That's when the Weizmann energy is bigger than the degeneracy energy of the electrons. But again, this is on a logarithmic scale, so this is an enormous order of magnitude magnetoresistance. And that was in a silicon MOSFET. Here's, I think, maybe particularly beautiful data on this on a 10 nanometer wide gallium arsenide quantum well. Here it's particularly beautiful in the fact that this saturation is really flat at high fields. And again, you see this order of magnitude rise of the resistivity when you polarize the electron spins. And it's, again, very hard to think of any conventional explanation of why taking a Fermi liquid and polarizing the spins should make an order of magnitude increase in the resistivity. In fact, you might have thought it would make a decrease in the resistivity, because you would now have a bigger Fermi energy. So for most scattering processes, that would mean you would have a longer mean free path. And here's trying to find a way of presenting the data as dramatically as possible. Here's this case, the conductivity as a function of temperature at 0 magnetic field. And here is the conductivity as a function of temperature at a magnetic field sufficient to polarize the electron spins. And so what you see is polarizing the electron spins has really quenched all the temperature dependence of the resistivity. If I had just seen this, we might have said that that's not unreasonable for some sort of dirty Fermi liquid. Okay, I guess I got a little carried away. I wanted to show you that similar sorts of behaviors are seen by a variety of different people in a variety of different systems. Yes?
Steve, if I naively just say that you have a conductivity which is 10 times E2 over H, because KFL in your system happens to be of that order.
Right.
I don't know anything about localization.
Right.
And what you do as a magnetic field is that since your KFL is larger than 1, you should have a positive orbital magnetic resistance and lose it.
You mean weak localization effects. If KFL is 10, weak localization effects should be tiny.
Yeah.
All of these things, these are big effects. These are not weak localization effects.
Yeah. No, I'm not talking about weak localization, but do you know the most naive way of thinking about resistivity is to ask what is KFL, and if you have a conductivity which is like 10 or 15, KFL is much larger than 1.
Right.
And then you have magnetoresistance because your system is not that dirty. Because
remember, this is spin polarizing. This is magnetic field in plane.
so this is not orbital at all.
This is not, I mean, you get actually fairly similar effects for a perpendicular magnetic field, but that gets complicated because you get into the quantum Hall effect as well. But let's just put the in-plane magnetic field where it's, and in case you doubt it, I mean, otherwise, why would you get this saturation? So I think this really is very clearly a spin effect. So we're getting this huge magnetoresistance just by polarizing the spins.
So there can be another effect because there is some finite thickness to the 2 to here, for example, 10 nanometers, and once the magnetic length
Yeah.
is comparable, you will start creating elliptic little Fermi.
Yeah, so you in fact see that when they do these experiments on wider heterostructures, you see some wider quantum wells, you see some magnetic field dependence here at the higher fields as well. So I think this is narrow enough that apparently the orbital effect is negligible here. I mean, if these were subtle effects, I would worry about these things. But, as I said, this is an order of magnitude effect. There's nothing subtle here. Okay, yeah.
What's the limitation on temperature? How low temperature must be to see that?
Yeah, I mean, you don't see this when the temperature, as long as the temperature is below the Fermi energy, the naive Fermi energy, you see this. And I don't remember just how it goes away with temperature. I'm not sure it's been looked at that carefully.
Sub-Kelvin.
What?
Around Kelvin or lower.
Yeah, well, in some of these, there were different, I don't know if here. So some of these have Fermi energies as high as 7 Kelvin. Some of them, these gallium arsenide ones had Fermi temperatures around 1 Kelvin. So for these, you had to be below 1 Kelvin. But I don't remember, honestly, how the magnetoresistance goes away with temperature. Which way am I going? Wrong way. Right. So I think that this phase is very difficult to explain in terms of any Fermi liquid. Any effects you would get in terms of Fermi liquid would just be weak compared to these large numbers. And this is in a regime, if this were in a regime where rho was comparable to rho Q, I would say, okay, we don't know what a Fermi liquid should do when the mean free path is on the order of the Fermi wavelength. But this is in a regime where, in some sense, the transport is already highly coherent. And this is for temperatures much less than the Fermi energy. And yet the resistance has this very strong temperature dependence. Polarizing the electron spins totally quenches this anomalous behavior. There's 1 or 2 orders of magnitude larger drag resistance than you would expect based on Fermi liquid considerations. I won't bother to walk you through that. There's some really weird thermopower that I don't even understand what the declarative statements are. And as far as I can tell, the cleaner your sample is, the more pronounced these anomalies become. So it really looks like it's telling us something about the behavior of the system in the clean limit, although, of course, all of the experiments have a finite amount of disorder, and that disorder is certainly affecting what's being seen. All right, so that's really the important thing I wanted to tell you, but let me tell you some speculative ideas that we have about what some of the physics is that might be going on here. So the question is, yeah?
Are the spectral properties of the signal particles known in this?
No. I mean, more or less what's known is the resistance. Okay, you can measure the resistance in different ways, drag resistance, Hall resistance.
But there was also a thermodynamical measurement.
There's been some compressibility looking for interesting things at the metal insulator transition, but I don't know. Well, I'll show you one. What? Yeah, but it's not clear what you want to look for in this anomalous metal. Those were looking for features at the metal insulator transition, which is not the focus of what I'm discussing. So let's ask the question, if we had no disorder, is it really true that we only have a simple Fermi liquid and a Wigner crystal, or might there be other phases that we can understand theoretically as we, say, increase RS that are intermediate between the simple metal and the Wigner crystal? And we have a sort of theorem that's very suggestive that such phases exist. So here's some phase diagram. Here's RS. Here's temperature. Here down at small RS, I have my Fermi liquid. Here up at large RS, I have my Wigner crystal. There's going to be some phase transition line. I've drawn this with a funny shape here. I'll explain that later. And then, of course, there's also maybe magnetism within the Fermi liquid. I think there are reasons to think that maybe at very large RS, it's a ferromagnet. People have conjectured that near the transition, maybe there's all sorts of ring exchanges that give a spin liquid. Maybe there's a two-stage thermal melting. Maybe down here, the Fermi liquid is unstable by Kohn-Lettinger to a very low temperature superconductor. Okay, those are subtleties. What I really want to know is what goes on here. Yeah?
The ferromagnet, you put it deep into the Wigner crystal.
Yeah.
But couldn't there be a Stoner transition at far lower?
There could be a Stoner transition in the metallic phase. There could be many other magnetic phase diagrams that you could draw here. So what I want to do is to tell you two simple, I call them theorems. I've now collaborated with mathematical physicists, and this is not a theorem, but it's something that I think has very compelling mathematical basis. So unless somebody objects, I'm going to call them theorems. And here's what I want to tell you is that if we have long-range interactions where the interactions fall off like 1 over r to the x. By long range, I mean it's non-integrable. So in 2 dimensions, that means that it falls off with a power law that's less than or equal to 2. But this theorem applies for the range between 1 and 2, that there are no possible first-order phase transitions. Rather, if you think there's a first-order phase transition, there must be an intermediate microemulsion phase. That's the first theorem I'm going to show. And the second theorem is that it's the same statement, but for the range of x between 2 and 3. This is not long range in the technical sense. It's integrable. So the way of proving these theorems is entirely different, but the statement of the result is the same. And of course, there are two important cases here. 3 is dipolar interactions, so maybe that's relevant to an electron gas with a screening gate, and 1 is the Bayer-Coulomb interaction. So these are physically relevant interactions. So the reason this is interesting is that at least at 0 temperature with long-range order, according to Landau, you would think that the transition between the Wigner crystal and the Fermi liquid, or any homogeneous fluid, should be first order because they're cubic invariants, which means that the free energy density, or at 0 temperature, the energy density, there should be 2 curves that meet at a cusp at the critical electron density. And so that would be the conventional picture of how you go from a fluid phase to a Wigner crystal phase. And of course, because we have long range, if I have x less than 1, that is x less than 2, that is to say long range interactions, phase separation isn't a possibility, so you don't have to do your Maxwell construction here. But what I will show you is that nonetheless, there's a lower free energy state that I can construct. So there's going to be a proof by contradiction that this cusp can't exist. And I'm going to prove it for the case where x is between 1 and 2. The hard point is when x is equal to 1, and I will just wave my hands at that one. That requires a little bit more careful analysis. So here's what I want to do. I want to sit at, say, I'm at this average density here, and I want to construct a new phase. I'm going to try to construct something that has lower energy than this. And the way I'm going to do this is I'm going to first make a series of regions of width L, which is going to be big so that I can still use my macroscopic considerations. This is big compared to any correlation length. And so I'm going to make a set of stripes of Wigner crystal, Fermi liquid, Wigner crystal, Fermi liquid. And so this is going to cost me, it's going to cost me some surface tension times 1 over L. Then what I'm going to do is I'm going to take some electron density from the Wigner crystal and put it in the Fermi liquid. So I'm going to make the density oscillate. And so you can see that gains me an energy minus mu. Mu is the difference in these slopes here times delta. And then it costs me some energy because of the Coulomb interaction between them. The system is no longer neutral, so it costs me this energy, where this L to the 2 minus x you can just get by scaling, or you can write down an integral. And now what I'm going to do is I'm going to minimize this expression with respect to delta, and that gives me this expression. And you can see that since x is between 1 and 2, this is L to some negative power, which is the statement that I said that the system can't be macroscopically inhomogeneous if it has long-range interactions. This delta, this contrast goes to 0 as L goes to infinity. And then I plug that value of L, of delta, into this expression, and we get an expression that looks like this. And what you can see is that this, L to the x minus 1, x is bigger than 1, so this is a positive value of L. So if L is big enough, this energy is always negative, which means that I've showed you by contradiction that I can't have a first-order phase transition. If I take x goes to 1, then this becomes a logarithm, and the theorem goes through the same way, but it requires a little more work. Logarithms are work. Okay, so good. So there can't be a direct transition from a uniform fluid to a Wigner crystal, at least if it's expected to be first order. So therefore, there must be some intermediate phases. Now, just because I constructed the intermediate phases by this construction doesn't mean that that's all that means is there is a lower energy phase. There could be some even lower energy phases than what I constructed, but let's just take that hint and imagine that we have intermediate phases that consists of microemulsions of Wigner crystal and Fermi liquid. And then you could, of course, imagine all sorts of different orderings of these microemulsions. They could form stripes, they could form puddles, they could form fluids, they could form all sorts of things. And even the thermodynamics of this is very complicated. The transport theory of such phases would be a mess. And therefore, it's obviously the explanation of unknown transport behavior. But at least what thing is clear on, although it's a transport idea, it's clear, at least intuitively, that as I move through any such microemulsion phase, the viscosity or the resistivity, whichever is the relevant concept, should increase as the volume fraction of Wigner crystal increases. Okay, it's
opposite sync.
What?
But it's opposite, but it does opposite sync in this metallic phase.
Wait. So let's ask what happens to the volume fraction of Wigner crystal and Fermi liquid. So if we look at the Fermi liquid, we know that its energy density, its free energy density is going to be somehow its energy density times T times its entropy. And its entropy is small in proportion to T over EF. On the other hand, in the Wigner crystal, well, there are spins. And at least to the extent that I can ignore exchange coupling between these, which tends to be exponentially small at large RS, the Wigner crystal has log 2 of entropy. So uncharacteristically, the Wigner crystal, the solid phase, is the high entropy phase, and the liquid is the low entropy phase. This is like the Pomeranchuk effect in helium. Here's the phase diagram of helium-3. Here's pressure and temperature. And you can see that at this range of pressure, if I start in the liquid and heat the system up, it will freeze. And that's because of this log 2 of spin entropy per helium atom that you have in the solid phase of helium. So here in my microemulsion, my Fermi liquid or liquid version maybe has a free entropy that's small in proportion to T over EF, whereas the Wigner crystal has an entropy that's to good approximation log 2 per electron. And what that means is that as I heat my fluid up, it will increase the volume fraction of Wigner crystal. Similarly, if I apply a magnetic field, there's an m dot b term in the free energy. The magnetization of the Fermi liquid is small in proportion to B over EF, but for the Wigner crystal, at least when B is bigger than the temperature, all the spins are polarized. So again, as we apply a magnetic field, we cause the system to freeze. So the volume fraction of the Wigner crystal in the microemulsions increases with either increasing temperature or increasing B parallel. And to the extent that I can ignore the exchange interaction in the Wigner crystal, it even does it linearly in T and linearly in B parallel. Okay, and so, well, maybe I should, okay, there's one new thing. I got a few weeks ago a draft paper from Miriam Sarachek on silicon MOSFETs on this same large RS system, in which she optimistically claims to have proven the existence of these electron microemulsions. Okay, well, you know, these systems are complicated. I don't think anything is proven, but let me give you the argument. It's a sort of interesting result. So here's a picture of this in-plane variation with magnetic field. Here, these curves of the magnetic field dependence of the conductance, I guess, at different values of the magnetic field. Here, they're collapsed, and the important point about this is that she's able to extract a value for the saturation magnetic field. So the saturation magnetic field is the magnetic field needed to fully polarize the electrons in our system. So here's a picture of that polarizing magnetic field as a function of electron density. And so up here, it's more or less linear in the density. So at high density, it's more or less linear in the density. That makes sense, because there, at least thermodynamically, we're going to have something that looks like a Fermi liquid. For a Fermi liquid, the Fermi energy in 2 dimensions is just proportional to the density. And so this is when the magnetic field is equal to the Fermi energy. But what you see is that as you get to lower and lower density, getting into the regime where there are all these transport anomalies, this saturation field deviates up. The saturation field is bigger than you think, as if the Fermi liquid portion of the system has a higher density than the average density. Okay, so, I mean, all right, let me end.
Actually, I'd like to ask about your first sentence. You said you are now getting more and more confused about this. What confuses you? You presented it as if everything works.
Well, you know, I was somewhat lawyerly in my presentation. I think I told you all the things that I know how to do respectable theory on, and I presented them without ever trying to compare anything in juxtaposition with some qualitative features of the experiment. I have, since you pinned me down, every time I've tried to do anything quantitative, I have not been able to get things that work. So, and mostly, you know, when I started working on this, this seemed like a really good start, and it looked like there was a linear road towards understanding things. But, you know, well, I don't know how many of you know Boris Spivak, but Boris can think of more possible cases, and it just becomes impossible to make progress if you're thinking about all the possible cases. So I've hit a total roadblock. So that's a good reason to talk about it at a school like this. Maybe people who are less inhibited can carry this forward.
Are all experiments, are they giving the same results?
So I don't know of any experimental controversies in this field.
All approaches are giving the same result.
Okay, you know, I'm not sure I can say that. You know, what tends to happen in all these fields is if people do experiments and they don't get what other people get, they tend to think they've made a mistake and they don't talk about it. So I've not seen anybody either say or publish results that are different from these, but it's a small number of results. I think I've given more or less at least all the results I know of. Okay, let me leave it at that.
So what would set the scale, the spatial scale of the microstructure? You showed that there is a surface tension term, so it should be big. It should want to be large, right?
Yeah, so that's correct. Let's see. So let's see, what do I want to say here? Oh no, it was before, no, it was after this. Okay, good. So this is the expression that I obtained. Now this expression is valid when L, I've used thermodynamic reasoning. So first let's understand when this is valid. It's valid when L is big. Okay? When L is big compared to all the characteristic scales in the problem. That's sufficient to prove the theorem. Now, if you're a little more ambitious and you said, let's minimize this with respect to L, then you're going to get L that's going to depend upon, you know, sigma naught and A. So A is something about the strength of the Coulomb interaction, so that's something like E squared. Sigma naught is some complicated microscopic thing that we don't know how to calculate, but it's some number. Once we minimize this, we're going to get L that's of the order of a microscopic length. So the first caveat on this is even though I do this, it's past the regime of validity of the theory. Okay, if I do that, what you see is, well, if this is a logarithm, then I'm going to get a length that's going to depend exponentially on sigma naught over A. which means it can be anything at once. Okay, it's going to be e to some number, and I don't really know that number. Okay, if it was just that number, that would be okay. I would say, all right, that number is 1, and if it's 2 pi, I don't really care. But e to the 1 and e to the 2 pi, those are pretty different. So that's another one of these problems that I've encountered, that I don't really know how to push the theory forward because it's so sensitive to microscopic details that I don't know how to control.
Actually, about that, are there any experiments with the screening gate to try to see what happens?
Yeah, so that's something I would love to have done. All of these experiments, I mean, even the MOSFETs, the screening gate is far away. It's, I think, 1,500 angstroms away. But there's no reason in principle you couldn't do these experiments with much closer screening gates. Then you have the dipolar interaction. For the dipolar interaction, you also have an exponential dependence on parameters, which is a problem, but at least it should be different.
Right.
Actually, the Blaznikov experiment wasn't it done with a bilayer with a very small separation? And Coulomb drag?
The Coulomb drag experiments are.
No, I'm not talking about the thermodynamical measurement of the mu dB.
Of the compressibility, yeah, you may be right.
Mu dB.
The mu dB, you may be right.
I think that one had.
Yeah. I mean, we get similar expressions for the two cases, but they mean very different things. So there should be, for instance, this delta is much bigger. So here delta is small. So the charge density contrast between the Wigner crystal and the Fermi liquid regions is small. In the case where there's dipolar screening, these regions more or less are determined by a Maxwell construction. So the density differences should be very big, and so, for instance, that should affect drag enormously. So, I mean, it's a really good question, but I don't know of systematic studies of that. Yeah.
So looking on these red and blue graphs, wouldn't an experimental observation would be that there would be fluctuation of compressibility in space?
Sure. No, if you could visualize these things, that would be the most direct way to see this. Any sort of visualization of this structure.
Steve, do you have any statement to make about possible hysteresis in your scenario? If you have chunks of bigger crystal inside the liquid, go back and forth, have anybody looked at, or would you expect for?
I mean, so there's no first order transition here. So for the clean system, I wouldn't expect hysteresis. Now, there is disorder, and once you've got these, icebergs floating around in your fluid, you would think these icebergs are very easily pinned, and jammed, and you might expect all sorts of hysteretic effects. But, I don't know how to make a clean theoretical statement about them, so.
Okay, so Aris didn't see me, but you did. Could you say then a bit more on the maybe about the hydrodynamics? Okay, let's say we accept all of this. Could you expand on why a hydrodynamic description might hit the parts that other descriptions don't reach?
Yeah. So all my language was hydrodynamic in effect. I was, in transport theory, in Boltzmann transport theory, what you care about is the nature of the elementary excitations. In hydrodynamics, what you care about is the nature of the fluid. So although I didn't do a hydrodynamic calculation, if you wanted to try to do anything else, you would have to say, what is, think of a droplet of Fermi liquid moving through a background of Wigner crystal. Think of that as a quasi-particle and write down a Boltzmann transport equation for that, which I guess in principle you could, but that's a pretty complicated object. All right.
So if there is this electronic Pomeranchuk effect because of entropy
Yeah.
in the crystal and from liquid, can one build a breach based on that? Pump on electrons?
Yeah, probably, that's right.
See, well, I mean, this would also be a proof of what.
Yeah, yeah, yeah. That's a brilliant idea.
Some coloring. I mean,
Yeah.
people
Yeah.
might have tried that somehow.
There's some people here who might have tried that, but nobody's jumping up and down. That's a brilliant idea. Yeah. I hadn't thought of that, but.
Maybe we could just repeat what the idea is.
Right. Yeah, so the Pomeranchuk effect in helium is used as the basic basis of a very effective type of refrigeration to low temperature. You have this backward sloping melting curve. So if the same thing is going on within the electron fluid, then you could use thermal cycling to cool the electron fluid by exactly the same effect.
So continuing on Andy's question, so if you now make the connection to hydrodynamic effects, other hydrodynamic effects that we might see, like Poissy flow and so on, what will happen if you try to flow this thing in a channel or
No, look,
to any other hydro?
yeah, so look, hydrodynamics is universal. So what happens is all of this complicated physics, if you're in the hydrodynamic regime, all of this complicated physics enters the hydrodynamics through the equation of state and the viscosity. Okay, now I've given you a reason to think that the viscosity itself might have strong singular temperature and magnetic field dependences, but other than that, it's just hydrodynamics like anything else.
But we have a prediction about the viscosity, because there are ways to measure viscosity.
Yeah, so only this, that they will have this singular temperature, roughly T-linear and B-linear temperature and field dependence, and that it will almost certainly be that the viscosity increases linearly with temperature, although I don't even really have a theory of that. It could be that it's got to be linear in T and B, but it could be for some bizarre reason in the opposite direction.
Okay, so that's.
I mean, if you want to think of exotic things, think of a droplet of Fermi liquid in a Wigner crystal. That's a good thing to think about because presumably the number of electrons in that droplet is quantized, since the Wigner crystal itself is a solid. And that means that it could either be a boson or a fermion, but it could easily change its character by changing its size by 1. So these could either condense into a Fermi liquid or condense into a charge 12 superfluid.
Okay, so let's see you again.